Thank you very, very much.
It's a bit of an intriguing title, but I think you'll understand uh, why as I go along. So, my core research is about giant black holes that we find in the centers of distant galaxies. And just to introduce that, astrophysicists study the cosmos using the whole electromagnetic spectrum. And also, they study the cosmos using neutrinos, which are these elusive particles that interact very weakly with anything. And so it's very, very difficult to detect them. But now, with new technology, we can. And they tell us a few different things about the cosmos than just the electromagnetic light. The electromagnetic light, of course, spans the whole spectrum, and we do have telescopes that can sense light from the cosmos, right from radio waves to infrared, visible light, ultraviolet, X-rays, and gamma rays. And we can learn about the cosmos from all these different frequencies. And we need to do that because they tell us different physics. And finally, we of course, since a few years, we are able to listen to the ripples in the fabric of space-time. Namely, we're able to detect gravitational waves, and that is a very new window and an exciting window that we have opened into the cosmos. So these are all, this is a glimpse of all the different kinds of telescopes that we use. This is the Venugappa Observatory, which is operated by the Indian Institute of Astrophysics, which is a visible light telescope. The Hubble Space Telescope, which is very famous, is also a visible light telescope. And this is AstroSat, which is an Indian satellite which observes the sky at ultraviolet as well as X-ray frequencies. This is the Chandra X-ray telescope from NASA, which is, of course, X-rays. This is the Spitzer infrared telescope. This is IceCube, which is in Antarctica and detects neutrinos. This is a picture of the Gravitational Wave Observatory. And this at the bottom, I'm sorry, is the giant meter wave radio telescope, which is outside of Pune and operated by TIFR. So one thing that I wanted to explain was that I will be showing you images of the cosmos. When they're not real images derived from real data, I will say that. But if we are observing real images at frequencies that we cannot see, how do we then render them, right? So that's a question. There are multiple ways of doing that. But one very popular way, which is also very evocative way, is to use what we call false color pictures. So here on top is a very famous galaxy. It's known as the Sombrero Galaxy, and this is a picture of it in visible light, but taken in with a very powerful telescope, so you can see a lot of detail. This is a picture of a cat as you would normally take it. Now, suppose you took an infrared picture of a cat. We cannot see infrared. So this is, I claim that this is infrared, a picture of a cat. So what does that mean? What it means is that each color doesn't represent a real color. It instead represents the intensity of the light at that frequency. So this is an infrared picture. So each color represents the intensity of infrared light. So then you see that the predicted thing happens, right? We know cats' noses are cold, so there is less infrared from there. The eyes and ears are warm, there is more infrared from there. So here orange represents more and white represents less. So the colors are arbitrary. And so just to illustrate that, here is another infrared image of a cat, but this is a different rendering, as in it is showing the same phenomenon that the nose is cold and the eyes are warm. It's just that the renderer has used different colors to represent those data. So a false color picture must be accompanied by a key which tells you which color is what. So this is just a digression to tell you how we render images that are not taken in visible light and which may be taken in X-rays or infrared or gamma rays or something. So just to illustrate that, this is the same Sombrero galaxy, and this image is an X-ray image of that galaxy. The green is the visible light image but in false color, and this is the infrared image, and you can see that the three different frequencies show us very different things. So the visible light image is the same as before. In the X-ray light, you see all kinds of X-ray emitting stars which you don't see in the visible, and here in the infrared we see all the emission that is coming from dust particles. So the dust particles look very dark in visible light. They look they're not seen at all in X-ray light, but in the infrared light they emit light, and so because they're warm particles at a few thousand degrees Kelvin, and so we see the dust in the galaxy in the form of a ring. So this is just to give you an example of what false color pictures are. So so now I'll come to what black holes are. So what are black holes? Black holes are chunks of space-time from which even light does not escape, right? So I can use that word escape to illustrate what it means using our high school concept of escape velocity. So we all might remember the formula we learned in high school for the escape velocity, which is a relationship between the velocity and the mass and the distance from the center of the gravitating body was the constant. And we all know that when if we throw something, it will fall back to Earth. If we throw it faster, it may fall a bit further. And if we throw it really, really fast, it will escape the gravity of the Earth and get launched into outer space. And that escape velocity for the Earth, given that this is the distance between the center of the Earth and the point from where you might launch it, that escape velocity is about 11 kilometers a second. And for the moon, it is less because the moon's mass is less, and it's about 2 kilometers a second. So now, if we use this idea of escape velocity, and if we squeeze all the mass of the Earth into a smaller value, we know that the mass remains the same, but this changes, it reduces, and so the escape velocity will increase. So now, if we imagine that we squeeze it so much that the escape velocity becomes the velocity of light. Now, light is the fastest thing we know, and therefore, if we squeeze something to such an extent that its escape velocity is equal to the escape velocity of light, then nothing will escape from that. And that is what is a black hole. And so substituting that in the formula here, the straightforward formula, gives us a relationship between this r, which is the distance between the center of this mass we're looking at and the surface from where we are looking at escape velocity, and the mass of that object. So it turns out that if we were to imagine that we squeeze all of the mass of the Earth into a marble size, then it would become a black hole. Then it would satisfy this relationship. Then the escape velocity would become 300,000 kilometers per second, and it would become a black hole. Now, Einstein proposed his theory of relativity in 1915, and this was a very novel way of looking at gravity. So not looking at it as a force, but instead saying that every mass, every single mass, whether it's my water bottle or me or your desk or your university building, every mass curves space-time. And so therefore, any test particle, shall we say, or a small, so this diagram just illustrates how the Earth might curve space-time. But it is not only very massive objects that curve space-time, it is every mass, like I said, except that this space-time is a very stiff and tough thing, and so it is very difficult to actually curve it. And so the amount that, say, my mass or your university building's mass will curve space-time is extremely, extremely small. But something like the Earth can curve it to a significant extent. And as you can imagine, something like a black hole will really curve the space-time very heavily. And this was put very nicely and very intuitively by somebody called John Wheeler, who said that the general theory of relativity according to the general theory of relativity, mass tells space-time how to curve, and space-time tells mass how to move. Um, Now, very quickly after Einstein proposed his theory of relativity, somebody called Karl Schwarzschild predicted a consequence of this theory, where he derived a relationship between size and mass, which was exactly like the relationship I showed you earlier, which was using the idea of escape velocity and equating it to the velocity of light. So, was that a black hole? Now, today, general theory and its consequences are a matter of everyday life for us because, for example, our GPS systems on our cell phones wouldn't work if we did not take into account general theory of relativity. But at the time, there was a lot of skepticism about this. So the consequence that Schwarzschild derived was not trusted. It was seen as some sort of mathematical construct. Many years later, Robert Oppenheimer of the atomic bomb fame investigated what would happen when stars collapsed once their fuel was exhausted. And he found that stars could indeed collapse into something which had infinite curvature in the space-time sort of language, which meant that what Karl Schwarzschild found was something like a black hole. Those days that phrase wasn't used, but Oppenheimer correctly interpreted that this radius that he derived represented a surface of a sphere, which was like an information horizon, saying that uh, when a star collapses like this, it will close itself off from any communication with observers outside that sphere. And so the only thing that an observer outside that sphere can sense is the gravity and nothing else. But nevertheless, there was a lot of skepticism about this because this was just a mathematical construct, and people don't like singularities. Singularities are things where there is the curvature becomes infinite, and one doesn't know how to deal with that, so people don't like that. And so there were these many questions which remained. Are these objects really real? Is it an artifact? And would the matter eventually just come out? Could quantum physical effects prevent this kind of a collapse? So this skepticism went on until the early 60s, when a very strange object was discovered in the sky. So here is a picture that shows that, and you can see a lot of pinpoints of light, which are, stars and so on. And this pinpoint in the very center, it looks like any other pinpoint, but it was very different because it had a spectrum that was very, very different from any star that was known until then. And it was a person called Martin Schmidt who realized that the spectrum looked very different simply because it had been shifted to a large extent. And actually, the lines that were being seen are the familiar lines that we know in the laboratory, the Balmer lines, the oxygen 3 lines, and so on. So was all well? No, because if these lines were indeed familiar lines, it meant that this object was extremely far away. And if it was extremely far away and we still saw it like a star, it meant that it was extremely luminous. So here was an object which was unexplainably luminous. There was no phenomenon we knew of which could generate this luminosity. No star, no collection of stars, no exploding stars or collection of exploding stars. Nothing could explain this. And therefore, there was this poem that actually George Gamow wrote, saying, "Twinkle, twinkle, quasi star, biggest puzzle from afar, how, unlike the other ones, brighter than a billion suns. Twinkle, twinkle, quasi star, how I wonder what you are." Because the amount of light that it emitted was more than the light from all the stars in our Milky Way or some neighboring galaxy like Andromeda or anything. So we did need objects like the kind that Oppenheimer had talked about, where there was this extremely strong gravity just outside a black hole, which could be harnessed to produce the kind of power that was being seen. The questions were still there, though, as to whether they were real and was it an artifact, and can matter come out, or can quantum physical effects explain it? But Roger Penrose came along and he had the answers. So he used extremely innovative topological methods. He did not apply any special assumptions, and he used his amazing geometric intuition to infer that, in fact, collapse into something like this was inevitable. So he didn't avoid the singularity, but the singularity was still there, but it was shielded from the observer. So you had the singularity in the center, supposedly, but you had a sphere around it, which was the size of the sphere was exactly as given by the formula of Karl Schwarzschild, and indeed the formula, the escape velocity formula. So there was this sphere which shielded us from the central singularity. So as empirical physicists, all we needed to worry about was what was outside of that singularity. What was inside was not very nice, because the moment you crossed that sphere, all paths led into the future, to the end of time, so to speak. So that was not something that was very nice, but nevertheless, since there was this sphere that shielded us from the singularity, we could sort of start to intuitively think about these objects. So many such objects were then seen. So from the centers of galaxies, there seemed to be this enormous power, which was more than all the stars of that galaxy put together. Not only that, from the centers of these galaxies, there seemed to be jets of plasma, which was squirted out. And sometimes they've squirted out with such high kinetic power that they were they had relativistic speeds, and they were launched into intergalactic space, which is what you're seeing in these images. So these are real images, both of them. They're false color. So this is showing a true color image of a piece of sky, which shows a central galaxy and also some stars and so on in the foreground, on top of which is overlaid a false color picture in pink and so on of the radio emission coming from these jets of plasma that are squirted out from the center of the galaxy and diffuse out into intergalactic space. Here is again a false color picture. In blue, it's a false color picture of visible light, which shows you stars and galaxies and so on. But from the center of this particular galaxy, again, you're seeing these jets of plasma, which are coming out into intergalactic space. And these this picture is taken from the film Interstellar. If some of you have seen that, it is a fictitious black hole called Gargantua, and it is the result of a computer simulation which shows what happens when matter comes very close to a black hole, gets sucked into the black hole, but swirls around before actually plunging into the black hole, swirling around, getting accelerated and therefore heated to very high temperatures. And it is this that generates plasma and magnetic fields, which result in the jets of plasma being squirted out. And we actually know that this is being squirted out because we have actually observed we've taken images of this plasma at different times, and we can actually see that these blobs of plasma are actually moving out, which is what this animation is showing us. The date is shown in the upper right corner. And this is a computer simulation of the actual phenomenon. So this is showing you, this is putting in all the correct physics that we know so far, general relativistic magnetohydrodynamics, and the green lines represent magnetic fields. So what it is showing is that when matter comes very close to a black hole, it is sucked in, but it is not sucked in directly, obviously, because all matter, or most matter is not going to be traveling directly into the black hole, but it's going to be traveling in some other direction. So the matter gets pulled and then pulled into this swirling spiral-like thing, eventually plunging into the black hole. But in the process, the matter is heated to very high temperatures. It generates light as well as plasma and magnetic fields. And so some of that matter is launched into intergalactic space, which is what this simulation is showing us. So this simulation is sort of telling us that this is a possible scenario of what is happening. Now, so far what I have told you is that we are seeing all these fabulous pictures of galaxies which have spewed out jets of plasma and it's just shining very powerfully, more than all the stars put together and so on. And we're saying that the only explanation for this is that there is a giant black hole in the center of these galaxies which is driving all these energetic phenomena. But that is still not direct evidence. Right? For direct evidence, we need to actually see that there is a black hole there. Of course, black holes can't be seen because they are black, but they are very massive objects, and therefore we should be able to see the impact, the effect of the black hole on things which are near it. And so that is the work that was done since the late 90s in the center of our Milky Way. So this is showing you the center of the Milky Way. The center of the Milky Way was seen as the best place to look for such giant black holes and the gravitational effects of such giant black holes. The challenges are two. One, that in order to get sharp images, or rather getting sharp images is not easy because of this phenomenon here, shown here on top. Because around the Earth is the atmosphere. A light ray coming from the cosmos should actually come straight onto our telescope, but it doesn't because there is this atmosphere which has refractive index changes, and so the light ray is made to dance around a lot before actually landing on the sensor. And so what one would get is something like this on the right, that is these multiple images of stars. But this is happening very fast. So in an ordinary picture that we are trying to take with an ordinary exposure, we would actually see a blur and not these individual images because this is happening very fast. So this is one challenge of observing things which are very far away, and similarly observing what is the center of our Milky Way. The other challenge is that because we are looking right into the Milky Way, there's a lot of dust particles in our line of sight. I mean, lot of is wrong. It's almost vacuum out there, but and there are very, very few dust particles per cubic meter or something. But when we're looking at these vast distances, and the center of the Milky Way is 26,000 light years away, there's a lot of dust particles then in our line of sight, and those prevent us from seeing the starred light behind because dust particles scatter the light in all other directions. So what is the solution? The solution is to look at the center of the Milky Way either in radio light or infrared light, because dust particles are transparent to these two things. So that was what was done by this astrophysicist, Andrea Ghez, who used a telescope in Hawaii called the Keck telescope. It has got a very, very large mirror, a 10-meter sized mirror. And the advantage of using that was that she could beat this dancing around of the light rays that was happening. Because she had this large mirror, she could collect a lot of photons in very short exposures. And so she could take very short exposures which would catch the light ray, so to speak, before it did this dancing around. And so she was able to measure stars at the center of the Milky Way, and not only that, measure their movement by monitoring them every so often. Another team led by Reinhard Genzel from Germany was doing this very similar work using their telescopes in Chile. And after a while, Andrea Ghez and their team made one more technological advance. The telescope mirror, which is actually 10 meters in diameter, is not a single mirror. it is made up of these hexagonal segments, which is what is seen here. So this is a hexagonal segment, and they all come together to make this mirror. And the segments are there because you can then have things at the back of each of these segments to manipulate how they're oriented. And so this was one step ahead in that, so the atmosphere is creating these disturbances, which is making the light ray dance around. The telescope is made to send out a laser beam through the atmosphere to measure what are these distortions and then correct the mirrors to compensate for the distortions in real time. So it's a very, very fast process, of course, but very successful. So just to illustrate that, here's an image of the planet Uranus, and here is this image is without making corrections for the atmospheric distortions, and this is with making the corrections. You can see the increase in sharpness very clearly. So what Andrea Ghez did was to take these images at regular intervals and measure the movement of the stars near the center of the Milky Way. And I will show you their data, but just to explain, what I will show you is an animation of images like this, and this is a false color image. What you see as multicolor spots, each of them is a star. And what you see as a white star is not a real star, but it just marks that particular position, and you will see why it marks that position. And here, up here, is the date when that image was taken. So they took a series of images and put them all together to make an animation, and that is what I will show you next. And can you see the animation?
Yes. Yes.
Okay, so you can see that these stars are moving, first of all. Secondly, they are not moving in straight lines. They are not moving randomly. They are all moving in elliptical orbits around the same point, which is marked by that white star. In fact, very reminiscent of our own solar system, where all the planets are moving around the sun. And so those are very familiar Keplerian orbits. And if there is a bunch of things which are undergoing Keplerian orbits, then we know that there are three quantities which are related: the mass of whatever is driving these orbits, the speed, and the distance or the size of the orbit. So the mass is of course unknown. It's something dark that we are not able to see, and we only able to tell that it is driving the stars in elliptical orbits. But the size of the objects can be measured and the speed can be measured because they have taken these images over a period of time. And so using this, they inferred that there is a black hole in the center of our Milky Way. Why is it a black hole? Because if you look at the nearest star that is making this elliptical orbit, you see that it's going very close to this dark object and then emerging in its elliptical orbit. It's not sort of colliding and deviating. So what that means is that whatever this dark object is that is driving these things has to be smaller than the distance of closest approach. So this means that a very, very large mass is concentrated in a very, very small volume, and only a black hole can meet that condition. So they concluded that the black hole at the center of the Milky Way has a mass that is 4 million times the mass of our sun. And this got the Nobel Prize, as you all know, last year, this discovery. And the Nobel Prize went to Roger Penrose, whose theoretical work I mentioned earlier, and to Reinhard Genzel and to Andrea Ghez. So there was a lot of noise in the media that was made about the fact that Andrea Ghez was only the fourth woman to get the Nobel Prize in Physics. So Maria Skłodowska-Curie got it in 1903. Maria Geertz-Meyer got it in 1963. That was 60 years later. That was the second woman to get the Physics Nobel Prize. And then Donna Strickland got it in 2018. That was again many, many decades later. And then Andrea Ghez got it in 2020. So why was this? So if I ask this question to audiences, they typically answer that, well, women have to take care of their families, and that is the reason why they don't get time to do cutting edge physics. So there are not a whole lot of women who do cutting edge physics. But is that really the answer? This was an article that the director of Keck Observatory wrote when Andrea Ghez got the prize. And the headline says, How Andrea Ghez won the Nobel Prize for an experiment that nobody thought would work. This director, he was actually head of the technical team at that time in the 90s when she proposed this work. Going back a bit, Andrea Ghez did her PhD from Caltech, which she submitted in 1993, and she dedicated her PhD thesis to all the women scientists she had known. So why would she do this? She has said that I grew up hearing the word no all the time. You're a girl, you can't do it. You're a girl, there's no way you can get into MIT or Caltech. And if you look at the way science has progressed, there are all these other women, Lisa Meitner, Chien-Shing Wu, Bibha Chowdhury from India, Vera Rubin, and Jocelyn Bell, who have, these are just a few names that I have chosen, who all did transformational work in physics. And nobody would argue that this work did not receive the Nobel Prize. In fact, Jocelyn Bell's work received the Nobel Prize, but it was only given to her PhD supervisor, and she was not given the prize. So clearly, it's not because women have to spend a lot of time caring for their families. Women are doing excellent work, but they're being denied the Nobel Prize. And that was also echoed by Andrea Gez's experience, where she said that she was hearing no all the time. So then, why is there a gender gap in science? Can we look at what the data from India tell us about this? Here are listed the typical reasons that are given to explain the gender gap in science. One is that there is a lack of interest in science among girls. Another is that there is lower competence among women. A third is that girls are socialized to think that they are incompetent in science. A fourth is that discriminatory familial responsibilities on women prevent them from doing work in science. And the last one is that there is discrimination within the profession, which is what I've hinted at from before. So what do the evidence tell us? So before looking at the evidence, I wanted to remind us that sex is biological, but gender is socially constructed. In other words, we learn to be men and women. So a social construct is something that does not exist in nature, but is invented by society, and we all act as if it exists, and by our tacit agreement, it does exist. So in the gender arena, some examples of social constructs are, for example, that men should not wear saris or skirts. Another example is that women should not drive or don't drive buses, or women don't play the nadaswaram. Here is a picture of somebody called Mamata from Bengaluru, a picture taken at an astrophysics outreach event to which she came during March for Science. And Mamata is a bus driver. And here is a picture of Kali Shabi Mehboob playing the Nadaswaram. She got the Padma Shri in 2020. So clearly, so let us look at each of these points. What about the evidence for a lack of interest in science among girls? So we know about the Inspire student fellowships in science, and more girls than boys win this fellowship. In physics, it's 50-50. In all of science, it's 57%. The Indian Academy of Sciences has summer fellowships, and more than 60% girls win this fellowship. So it can't really be that there's a lack of interest in science among girls. This is a survey done of 4 schools in Uttarakhand, in Dehradun actually, and in these schools, a minimum of 30% girls said that they like science subjects. So it can't be this. So is it lower competence among women? So again, the Inspire faculty fellowships are won by almost 40% women, which cannot happen if women are really of low competence. A study by Kumar in 2001 of scientists in science institutions showed that there was no productivity deficit among women. A study by Jayashree Subramanian in 2014, again of scientists employed in science institutions, showed that there were more women who were rank holders in their universities, and there were fewer women than men who had lower rank. So clearly it's not the lack of competence. What about the idea that girls are socialized to feel incompetent in science? So again, going back to the Dehradun study, the students were asked about the perception that fewer girls than boys are interested in higher studies in science and maths, and more boys than girls said yes. The more girls than boys said no, and more boys than girls said don't know. Again, the perceptions that girls are not good at science and maths, or science and maths are difficult and girls go for easier subjects, were also looked at, and again it was more boys than girls who felt that way. So it's not so much, shall I say, that girls are socialized to feel incompetent in science as much as boys seem to be socialized to think that girls are bad at science. So that is a problem. What about discriminatory familial responsibilities? So there are a large number of women who've made use of the government's career break fellowships in science, which suggests that the discriminatory familial responsibilities are a major factor negatively impacting women. There was a global survey of physicists done in 2014, where for India, more men than women reported being in a long-term relationship or or being a parent or guardian, but more women than men reported that careers influence their personal decisions. So this also suggests that discriminatory familial responsibilities on women rather than men might negatively impact women. Again, Neelam, I'm sorry, yeah. So while that is true, the fact that the gender gap in some disciplines is worse than in other disciplines does not support this idea. So clearly, discriminatory familial responsibilities cannot be the whole story, because the gender gap in physics, for example, is much worse than in, say, biology. So I'm only going to put a dotted ellipse around this. Now, what about discrimination within the profession? So there's a slide which was out of place. So there is a study by Kumar, 2001, which I referred to earlier already, where she showed an inverse correlation between gender and position in the hierarchy for science institutions, comparing men and women scientists. She also showed that the mean age of women who were professors or equivalent was significantly higher than that for men. And this is while there is no productivity deficit. There's no difference in publications between the men scientists and the women scientists. So clearly there is discrimination within the profession. Similarly, we looked at some statistics for physics. So the physics PhDs employed in higher education in India are about 20% women. This is statistics from a couple of years ago. Whereas if you look at the Indian Academy Fellowships, it's only 6%. The prestigious C.V. Raman Memorial Lectures, the fraction is only 4%. And in Physics Institute governing councils, it is only 3%. So it does drop very drastically when it comes to prestigious things. So the point here is that we can ask the question, why is it only 20% in higher education? That's a separate story. But even if we take that at face value, there are 20%. Women. Why should that fraction change when it comes to academy fellowships or the Raman Physics lectures or governing councils? So there's clearly discrimination within the profession. So one effort in order to address this was something called the Gender and Physics Working Group of the Indian Physics Association, which I proposed in 2016, and to the Indian Physics Association. It was formalized in 2017, and we had this conference called Pressing for Progress 2019 in Hyderabad, to which Jayashree came, and she mentioned that conference. So one thing is that once this working group was launched, this prestigious C.V. Raman Memorial Lectures, which showed a very small fraction of women earlier, now has increased, and now roughly 30% of the lectures, the C.V. Raman lectures, are given by women scientists. Similarly, the R.D. Birla Memorial Awards of the Indian Physics Association had never been given to a woman until 2017, and for the first time last year, Bimla Bhuti won the award. So we're very happy about that, and we're happy about the fact that this kind of interventions actually work. So that is important. So we are a flawed meritocracy. We need to fix it, but we have to remember that we cannot be fixing the women. We cannot be making interventions in order to so-called improve their skills or their confidence and so on, instead of looking at what is the cause. The cause is that we have an enterprise which is not welcoming of women. It is probably not welcoming of many other discriminated groups. So our enterprise needs to become one where people of all genders feel welcome. So that is what we need to do, and not fix the women. So from this conference called Pressing for Progress in 2019, the Hyderabad Charter for Gender Equity in Physics emerged, and this has a whole bunch of recommendations, which I'll talk about very briefly, and then I will take questions. So there are many endorsers of the Hyderabad Charter. Many leaders of institutions or past leaders of institutions have endorsed the charter, which is very heartening, and so it makes us hopeful, because the buy-in from leaders of institutions is essential in order to change the working climate in our enterprise. The Hyderabad Charter is based on these very fundamental principles. Firstly, people of all genders have equal potential to excel in all aspects of physics practice, and utilizing the talents of all is essential for the physics enterprise to achieve its full potential. So I don't think anybody would argue with these. Now, some of the recommendations are as follows. So any work-life balance policy, such as childcare leave or mobility schemes, we recommend should be gender neutral, because whatever interventions, maybe I'll go through the okay, I'm missing a slide on the guiding principles of the charter. One of the guiding principles of the charter is that any intervention that you make, it should not reinforce the patriarchal attitudes, because patriarchy is one of the root causes of the gender gap. And so, for example, that is why I said that any work-life balance policies, such as childcare leave or mobility schemes, should be gender neutral. In other words, they should be open to people of all genders. There should not be workshops which are exclusively for women. So, for example, it's very common for both BST and UGC to fund workshops only for women, and they say they are to enhance their research skills and or sensitize them to legal issues, or there are even workshops for emotional intelligence, and this is completely patriarchal and it is not recommended. So, if at all, there should be workshops for gender sensitization, and this should be for everybody. So the point is that regardless of our gender, we are all raised to accept sexist thought and sexist action. This doesn't it doesn't exclude women. It is both men and women who are raised to be sexist, and therefore we have to counter that. So one way to counter it is to become aware of it, and workshops that sensitize us can make us aware of it, but it should be workshops for everybody and not just for students or mid-career people or early career people, but for everybody, right from the leadership and management down to all members of the enterprise. We have several recommendations for hiring. So we say that criteria for hiring should be formulated beforehand, and there should be no hidden norms or hidden criteria that should be used. The age bar for hiring should be removed, is what we are recommending. The hiring process should provide full information on all the steps and the timeline of hiring to all candidates. And very important, the status, the position, or the background of a life partner should not be a criterion in hiring. This is partly the reference to this business of hidden criteria, because it's very common in institutions to have such criteria where they decide on whether to make an offer to a meritorious candidate, depending on what the spouse or life partner of the meritorious candidate is doing, or where that person is, or which city that person is in, and so on. So we are saying that that is unacceptable and should not be done. So it's important to remember that the closing of the gender gap, meaning having equal numbers of men and women at all levels of physics practice, that is a necessary step. I mean, I'm saying physics here, but this applies to all sciences. It is a necessary step. It in fact applies to all academia. So parity of numbers is a necessary step to achieve equality, but it's not a sufficient one. Furthermore, we are saying that the practice of physics is a social activity, and so addressing gender bias requires insights from the social sciences. And therefore, we recommend that, for example, for graduate students in PhD coursework, there should be a course on sociology, on the sociology of science. And finally, when a process of selection reduces the gender fraction from what it is in the pool, it is a signature of a biased process. So all these things do need to be kept in mind. In classrooms and in mentoring, we recommend that all students should be held to the same standards, regardless of gender. And when we give career advice or when we mentor students, we should mentor them in the same way, regardless of gender. Right now, what happens is that when people give career advice, they give different career advice to girls than to boys. So to boys, they will say you have to follow your passion and you'll do this, that, and the other. But for the girls, they will say, but you have to be mindful that you'll get married, and how will you manage your family, and you have to work really hard, because only then you can manage both your family and your career, and so on. Now, the point is, caregiving responsibilities and household responsibilities are everyone's responsibility. So you should be giving the same reason to everyone, whether they are men or women. And this business about working hard is something that you need to do regardless of what profession you take, whether it is football or science or dancing. It doesn't matter. All professions require dedication and hard work and all that in order to excel. So it is inappropriate that only women are singled out to give career advice that they have to work hard. So these are some of the recommendations we made. I will stop by showing this cartoon, which was published in the Resonance magazine of 2017. So I'll take questions.
Thank you very much, Professor Shastri. It was a wonderful talk, and thanks for all the recommendations. So before opening up to the students, so I have a small query that so the kind of recommendations you are giving to the institutes like probably DSG, UGC, and so on. So do they come as a guidelines very soon, or what is the status as of now? I know that you have been working on this from past 2 years.
Yeah. So what I will do is I will stop the share, and I will paste the link to a publication about this, about the charter, which shows the complete charter, because I didn't show you um, everything. And so I would request that you at least email it to everyone present here. So what we have done with the charter is that we have we have sought endorsements for the charter from physics PhDs in the country, or affiliated with institutions in the country. We have more than 330 such endorsements, and we are continuing to seek them. So if there are any physics PhDs here in your university, and in the audience, or even if not in the audience, and would like to endorse the charter, please send me an email, and we'll be very happy to receive your endorsement. We have sent this in 2020, in fact on Women's Day 2020, to the Department of Science and Technology and to the Principal Scientific Advisor and all that. Some of our recommendations have got into the draft Science and Technology policy, and we are very happy about that. But more needs to be done, and DST does need to make its interventions gender neutral. We're working on that. We are in dialogue with people from DST. So we feel it should be a two-pronged thing. So there should be things from the top, of course, but this gives an opportunity for people to make bottom-up changes in their own local spheres and in their own departments and institutions. So, for example, one of the things we recommend is to have a gender audit. So all we are saying physics, but it applies to all departments, should have their gender fraction of faculty displayed on their webpage. So that is one step. Then another very easy thing to do is to correct all the official language and forms and documents, and even in everyday usage, to a gender neutral language. These are small steps which can make a difference, and then there are a whole lot more. So yeah, that is to sum up what I'm saying.
Okay. Yeah, thank you so much. So now any questions from the students?
Ma'am, can we just ask, or do we like have to raise hands and wait?
You can ask now.
Okay. Ma'am, I would like to ask you. You talked about introducing all these policies which are gender neutral. So once we do introduce such policies, it will ultimately boil down to, people having to sort of share the workload that is there in a household, whether it comes to rearing a child or whatever, like whatever household work. But there will obviously be resistance to that, right? So yeah, creating the policy is the first step. But what exactly do you think can an institution or a body do in order to go down to that level and sort of deal with that resistance more directly?
And no, I don't think so. So what we are saying is they cannot reinforce that. It is unacceptable to reinforce that. So it is unacceptable, for example, to say we will have flexible timings for women, because then that is saying, now that is something within your control, right? I'm sure tomorrow if your university dean or provost decides that, they can do it. They can make flexible time for women faculty. But we are saying that is unacceptable. You cannot reinforce a stereotype, because if you're saying that women will have flexible timing, you're saying women still have to do all the cooking and cleaning and caring. We will allow them to come a little late to work. That is not acceptable. So if you are going to have flexible work hours in order to improve work-life balance of your employees, when by you I mean your university, then you should make flexible timing available to everybody. So everybody then has the opportunity. So then they don't have an excuse, right? They don't have an excuse not to um, take full responsibility for running the household and caregiving of their parents and so on. We can't, of course, institutions cannot go interfere in personal lives, but if I'm addressing the students, I would say that, you need to change your life choices also. You need to look for spouses who, believe that caregiving is everybody's responsibility. Building a family is everybody's responsibility. Caring for elders is everybody's responsibility.
Thank you, ma'am.
Hello, hello, ma'am.
Yeah.
It's Asha this side. So, ma'am, you talk of general neutrality in public offices and on a workspaces, ma'am. But what's the point of a general neutrality at a point when women are at a position as far as a society is concerned, the position of women is way looked upon as way down the map. So isn't there a need to firstly uplift that, and once we've gotten to a point that women are equal to men, where the ideology of people have changed, then we introduce something like gender neutral laws?
No. So there is no question that gender inequity is very deep in our society. I don't disagree with that. I don't disagree with the fact that it is a huge problem. I disagree with the fact that we have to wait until that is solved in order to fix our scientific enterprise or academic enterprise. Because it's not like in our academic enterprise, we reflect everything that happens in outside society, right? For example, in outside society, there is drunken behavior, right? So do we say, oh, in outside society there is drunken behavior, so we will allow drunken behavior to happen in our institutions until that gets fixed? Are we saying that? No. We're saying here drunken behavior is not acceptable, right? There are rules about it. I mean, if somebody does it, then they can be penalized and so on. So it's like that.
So, ma'am, what I was saying was that firstly, before introducing the gender neutral laws, for as far as a society is concerned, isn't it essential that firstly laws are implemented so that women can be uplifted, the position in the society can be uplifted?
So I don't know why you're saying that. What we mean by gender neutral, it's not gender neutral laws. Okay, we're saying that if you are making an intervention, so the hiring process in academia is gender neutral or claims to be gender neutral, right? There is nowhere that it says that women will be valued lower than men. Nowhere it says that if you have a person, a man and a woman applying for a job, and they both have the same qualifications, you will still value the woman lower. There is no rule that's saying that. So our enterprise is gender neutral on paper. It is not gender neutral in practice because of this reason that in society we have very patriarchal mindsets, and we carry those mindsets to our workplace. And that is the reason why women are valued less than men. And this is not only by men, it is by women as well. I don't know if you know this experiment is very famous. It's sort of called the John Jennifer experiment. This was a very famous experiment done in the US where the experimenters concocted a CV of a person who has just finished a PhD and supposedly and is looking for internships, sort of thing. And I don't remember the exact detail, but it was something like this. So this was a fictitious CV. They created duplicates of the CV. Let's say they created 100 duplicates. Out of them, for 50 of them, they gave the name Jennifer somebody, and for the other 50 they gave the name John somebody. So in this case, people would think that the person is a woman, and in that case, people would think the person is a man. And they sent these out to academics in universities and asked them certain questions about the application. For example, how at what salary would you hire this person, or how would you rate this person relative to something else, and so on. They ask those kinds of evaluation questions, and they sent these CVs to these fictitious CVs to both men and women academics, and the result they got was systematically the CVs which had the woman's name were valued lower than the CVs with the man's name. Okay, and this was by both men and women. So this is the kind of bias we're talking about. So on paper, our institutions are gender neutral. So what we are saying is, if you want to address the gender gap and you think of interventions, then the interventions have to be gender neutral. They cannot be gender biased. So you cannot say that women will get flexible times. Women will get, maternity leave, for example. There should be parental leave for everybody. So both members of a family, both parents should be eligible for parental leave, so that both participate in an equal way in the care of the child. Or it could be elderly care. In fact, we are saying don't make it parental leave, make it family care leave. So it could be, for a child, it could be for elderly parents. For example, I don't know if you know but if you're a government employee in India today, then you're entitled to child care leave of 2 years over your career for a child up to the age of 18. But this is open only to women.
Right.
Right. So there, that is wrong. We are saying that is wrong. That has to be open to both men and women.
Yeah, in fact, that has also changed in the recent times. I just read that the childcare leave actually, it earlier used to be sort of a non-pay leave where you will be salaried while you take the leave, but it has now changed that your pay will be cut once you take these leaves.
I see. Okay.
Yeah, thanks a lot, ma'am.
I should update myself on that. I haven't actually.
Yes, Dr. Gopinath, you have raised your hand.
Hi, yes, ma'am. Hello, I'm audible.
Yeah.
I have a question which may be a little off track, but I just got this question because in the outside world, the gender disparity, everywhere we see that, but in India, things may get worsened because of the caste disparity as well. Like, so here we have a much bigger problem where the caste disparity adds to the existing gender disparity. So, for example, a girl coming from a higher, so-called higher upper caste, may be having a much more exposure to education than from a lower caste, so-called lower caste. So how are things in Indian perspective to be tackled, especially?
You're saying, so I understood your first part, but what was your final question?
Because the challenges may be much severe in India, in the Indian scenario where the caste-based disparity also adds in
right.
to that.
Yeah. No, there's no question about that. It's complicated. So, in fact, just yesterday, again to mark Women's Day, me and a few others organized a roundtable on what we call intersectionality. One thing is that intersectionality is not. So, let me first explain what is intersectionality. It is saying that there are these different dimensions on which human beings discriminate against others. So gender is one of them. In India, caste is a very, very important one. And then there are others like economic class, like adeptness in English language, which is relevant for jobs and things, and so on. So intersectionality says that if you are a person with more than one dimension that is discriminatory. So, for example, if you're a woman, you face gender discrimination, but you may also be a Dalit, in which case you will face caste discrimination. And these two dimensions interact in unexpected ways. So it is the opposite of what happened. This also came up yesterday because there were some mathematicians also on the panel. It's the opposite of what happens in set theory. Like in set theory, you talk about sets and you talk about intersecting sets. So in the intersection, the members of the intersection have properties of both this and that. Whereas in this idea of intersectionality, which is a sociological framework to think about discrimination, if you happen to be a woman and a Dalit, then you will get hit from both ends, and so you will drop out. So you will not benefit from any interventions that are in favor of Dalits, because it will be the Dalit men who benefit from the favors. You will not benefit from any interventions that are meant to address gender, because it will always be the upper caste women who benefit from that. So you drop out of both. So this is known as intersectionality. We just had a roundtable on that. It makes it very complicated. There's no question, but there is also no question that the problems need to be addressed together. So we cannot sort of say in a typical science way, we would say, okay, let's sort of segregate and let's deal with the simpler things first and the next thing later. No, in this case, we do need to deal with all of them together. And it's not unique to India. Caste is unique to India. In the US, for example, you have race, and it is a very similar phenomenon. In other places, you have class, and then you have discrimination against indigenous people, and so on. So although the specific discrimination, caste discrimination, is sort of unique to India, in other places also there are other dimensions of discrimination, and makes it very complicated, and it is extremely important to work together to address all of them together.
Thank you, Professor Shastri. We would like to really thank Professor Shastri for taking some time and then discussing all these issues with us. It was very nice to have here, ma'am. It's our honor.
My pleasure. Thank you very much.
Yeah, thank you so much. And